Well, again, Dr. Fox here again on the series of lessons on the AQA A-Level Physics course, and this is the Astrophysics unit. We're about 2/3 of the way through the course now, and everything on this slide here we've done so far, apart from the thing in the middle, which is the Wien's displacement law, which is what this lesson is about. Get a piece of paper, pick 3 of these, do some revision. Remember, there's no point watching these videos if you can't remember it. You can watch as many videos as you like, but it doesn't go in here ready for the exam. You've got to write it down. So get going with it, pick 3, do them, pause the video, and then we'll carry on. So here's the specification part. As I said last time when I did Stefan's law, we're now doing Wien's displacement law, which is actually these first sections here. I'm going to touch just a little bit upon the inverse square law as well, which is pretty straightforward really, and give you some really good teacher advice here on some of the pitfalls that might come along if an exam question comes up about this in the final exam. But really, I think this one's going to be fairly straightforward. Some fairly easy concepts, and the mathematics is significantly more straightforward than the Stefan's law as well. So get your notes, put this title again. What I'd like you to do this time is put this learning objective: to be able to apply Wien's displacement law at blackbody temperature to typical star. And this is the equation here, which is lambda max. It's the maximum wavelength, temperature T in Kelvin, constant. I put careful here. This is the constant. This is Wien's constant, 2.9 times 10 to the power minus 3. This is actually meters Kelvin, not millikelvin, and it's really easy to mistake them. And I noticed in the formula sheet they give you 2 versions of this, and it's one of the very few equations where they actually include the constant within the equation itself. So just be wary. Make sure that you just use this value here. If this is in meters and that's in Kelvin, that's why it's meters Kelvin. And then I'll touch upon blackbody curve and the assumptions about blackbody, and that's where I'm going to start. Okay, blackbody radiation. Effectively, imagine a ball or a box, a cavity that's completely black, and there's a little tiny hole. That hole allows emission to go in, any sort of a wavelength, any sort of electromagnetic radiation, and it's not allowed to escape. It's a perfect absorber. But on the flip side, it's also a perfect emitter as well. But the emission depends on its temperature. So if it absorbs everything that it's forming on it, it will get to a certain temperature, and once that's in equilibrium with its surroundings, therefore it will start to emit at a certain temperature. And this is where this graph on here comes in. You can see that at 2000 K, this is what it looks like, and this is a black body curve, it's called. And then at 1750 K, it starts to look a bit different, and you'll see that the peak moves to longer wavelengths the cooler the black body is, and the peak will lower and flatten as it goes that way, and that will go towards this way. This one here is just power radiated. It can be intensity, it can be power, it can be anything basically involves brightness, absolute brightness that is. And this here, I've just picked one that happens to be an infrared emitter of black body. That's what most people think about black bodies being infrared, but they can go all the way any part of the electromagnetic spectrum. But these are generally quite hot. 2000 K is still hot, and when it gets into very hot, as in 50,000 K, you'll see that they move through the visible spectrum, and that's why the AQA picked it, because it's in the visible part. And the equation, of course, links these 2 things together. Now, be careful. This picture here is not a picture of lambda and T. That's actually an inverse square law. So that's a law that just looks like, hang on, your way around, that way. That's an inverse law. This is actually wavelength versus, on this case, I think that's flux, but it can be power and it could be intensity, just like it says here. Spelling mistake here, Planck, German chap, he had a C in his name there, but that's how he derived this. The history behind it's incredible. He first invoked quantum physics to be able to explain and describe what was called the ultraviolet catastrophe. Go and read any book by John Griven about this history of this fantastic, fascinating story as well. And of course, there's another chap called Boltzmann who did a lot of work on this. And then Maxwell Boltzmann distribution. You may recognize this if you've done some other physics elsewhere. You don't need to know any of this. You just need to know that for longer wavelengths, you have a cooler temperature. That's it. As you can see, 5500 K here has a wavelength, approximately in the 500 nanometers. And as the temperature decreases, that wavelength increases. So they're inversely proportional to one another. Asked a little question here. What's the curve? here. And this here, not on this graph here, it's an inverse law. An inverse law that has a constant, so it's not quite the pure inverse law that you deal with, but that's the one that you're dealing with. In other words, as temperature increases, lambda decreases, and vice versa. So, what do questions look like? State and explain without calculation which of these stars is the hottest. So we've got P, Q, and R. We look at the wavelength. Where's our shortest wavelength? It's got to be this one. It's got to be P. Because Wien's law, state Wien's law, the shorter the wavelength, the higher the temperature. So therefore, all the three stars are hottest. You don't need any numbers at all. However, if you read off here, you could actually give a temperature. But this particular equation does not want you to state that. It wants you to state that you know the relationship between them, not the actual numbers. Okay, and those mathematicians get really frustrated with this sort of thing, but this is physics, and it's just the relation in the physical world. I just mentioned about what they appear like in the formula sheet before, and this is what they are. You can see it's 10.90 times 10 to the power of minus 3 meters Kelvin. Remember how it appears in the actual formula sheet is this, so it doesn't actually give you this alpha symbol. But don't get worried about this. This is exactly the same number as the number here. So it's given in quite strange. I just thought I'd warn you there. So when you look at the formula sheet, it is just the equation. Lambda max T equals 2.9 times 10 to the power of minus 3. Job done. Okay, and here's the part of the formula sheet we're interested in. And there it is. Again, this is, meters Kelvin, so be careful here. That's where it appears in the formula sheet, so you know where you can go look for it. I include this here because there's an awful lot of other data that's included. This is on the front sheet of the data sheet, and this is buried in the astrophysics section of the data sheet as well. This lens equation here has now been ousted out of the qualification, but I noticed some formula sheets on some websites still have it on there, so don't worry about that. If you're doing the medical unit, that's the one that's in the medical unit now. It's no longer in the astrophysics one. So here we go. Here's a typical question. Deneb is the brightest star in the constellation of Cygnus, as well as on a triangle. Black body radiation of Deneb shows a peak at wavelength of 3.4 times 10 to the power minus 7. So no need for any conversion of units there. Calculate the black body temperature of Deneb, give your answer to appropriate significant figures. So significant figures here, this is where you look for it. There's two significant figures, so whatever your answer is here in K, remember, it's just the first two significant figures followed by zeros. Don't get drawn into the fact that there's no decimal place. You can include all the numbers. This is a test of that. And of course, the calculation is dead easy. Lambda max T equals the Wien's constant. So just get that out. But remember, it's just those two numbers. Power output of Deneb is 70,000 times greater than the sun. Calculate the radius of Deneb, and there's the surface temperature of the sun. Of course, what they haven't given you here is the radius of the sun, and that's what you need to be able to do that full calculation, because this is Stefan's law, of course. Luminosity, you do a ratio of luminosity, so Deneb 70,000 times greater than the sun, that cancels out. Go and see my lesson on Stefan's law if you want to know how to do that. But this leaves a lot of students cold, going, oh, hang on a second, I can't do it, I haven't got the radius of the sun. Remember what I just showed you from the formula sheet. They do give you the radius of the sun. It's buried right there in the bottom left-hand corner of the formula sheet. Go and look for it there. They give you the surface temperature of the sun, which is not on the formula sheet, but they do give you the radius. That's why you can do that 3 marker. Go and look at your formula sheet, go and get it, do the calculation. And I'll show the answers in 3, and there we go. So there's the answers there. You can see there's the ratio that's come in here, and the ratio of the radii here, and then you end up with this getting the radii of 10 to the 10, which is fairly typical. Don't worry about that. That's a fairly typical answer. You see, Stefan's law is much more involved than the Wien's law. And there you go, 8.5 to the power of 3, or 8,500K. Do not include any more significant figures, because they will penalise you, because that's 3 marks. Look at these are equivalent 3 marks for each. Get the Wien's law stuff right. Okay, here we go. Bellatrix and Betelgeuse. You may recognise this from the stars that we've used before. Explain what is meant by absolute magnitude. Remember, the word 10 parsecs has to come in there. It's the magnitude at which they are. Which of the two stars are closest? Again, you can use m minus m. The larger negative number will give you the closest star. And then calculate the peak of the wavelength. We didn't do this one before. It's only 2 marks for that. You look at temperature. A Bellatrix, you get 22,000, and then therefore you can get the peak of the wavelength. And the answer is coming in 3, 2, 1. And there it is. Brightness of star, Betelgeuse. Bellatrix is actually a lot brighter, but only appears a bit brighter, so Betelgeuse must be closer. And there it is. There's again the Wien's constant, and you end up with 1.32 times 10 to the power of -7 or 132 nanometers. So we dealt with Wien's law and Stefan's law. I'd like you to just put it into concept that we've got these equations that are all interlinking with each other. So there's a lot of things about the star. There's the power output, there's the temperature, there's the magnitude, the apparent magnitude, there's the surface area, there's the distance to the star as well, but also its radius. So these are all interlinking, and this rather complicated slide will tell you. So I based it all around Stefan's, which I think is the core to this. Power, which is also luminosity. What is the unit of luminosity here? And then you can break this down to the area, surface area of the star, the radius of the star. The Stefan-Boltzmann constant is called there, but we just call it Stefan's constant in A level, and then temperature in Kelvin. Now that temperature is then related to Wien's law, which gives you a peak wavelength. So different car stars have different colours. So therefore you can get the power output at that particular wavelength there. Then, of course, you've got this. Now, put this with no arrow to this because this is not SI units. These are all SI units up here. These are not. The only link to here is this. The difference between this and this number will give you the power to which to raise 2.51 to tell you how many times brighter M is compared to another star. So, in other words, if I've got a star that is an absolute magnitude of 5 and another star with an absolute magnitude of 3, there's a difference of 2 between there. That means it's 2.5 to the power of 2 times fainter. The 5 is the fainter, of course, compared to the 3. That's the only way you can get the link from here. And of course, this distance here is in parsecs, so you'd have to do a conversion into meters to be able to get it to what I'm going to introduce next, which is this one, which we haven't seen before, which is the intensity equation, or the inverse square law. The intensity of light is inversely proportional to the square of the distance. Now look at this. It just makes sense. This is the luminosity, or the power, both measured in watts. And this is just a sphere of radius distance to the star. So it's almost like you're drawing a sphere around in which all the light radiates into. And we just want to look at one little square meter on the outside of it, one little square meter. And that'll give us the intensity, how many watts per square meter at that distance. I'll show you a slide in a second which makes it a bit more obvious. But I want to just hold it on this one, in that this here, this L is also a P, it's power output, L, luminosity and power interchangeable. This is the distance to the star. Now be wary, you can see it looks an awful lot like this one here. This is the radius of the star, little r, d, distance to the star. So whereas this is measuring the radius from the center of the star to the outside, this is measuring the distance from the Earth to the star, or from the star to the Earth, which is probably a better way of thinking about it. And this capital I here is intensity. This equation does not feature on the formula sheet. It is not there, but it's something you have to learn. I showed you it right at the start in the specification. It's there. You need to know it. So the intensity, the watts per square meter, is equal to the luminosity of the star at the star total power output divided by 4 pi d squared. In other words, the surface area of a sphere marked out with a radius of the distance to this. And of course, this distance here is not the same distance here. This is in parsecs. So you have to convert this into meters. This has to be in meters because this is in watts and this is in watts per square meter. So this is why I'm putting this all on the same slide, because there is, and this is why it's good to have a teacher describe this, because it's not obvious from this. This doesn't appear on the formula sheet, but yet it's in the specification. This is on the formula sheet, but it's not an SI unit. And this distance here is in parsecs. So just hammering that home. And this is a good little slide to describe what the inverse square law is. So you've got your star here, and imagine this square here. Look, they're using R. What a nightmare. D, distance, radius of any sphere. And as you get to one radius, you get to 2 radii, of course, the area goes up by the square because it's a square, it's getting bigger. And you go 3 radii, it's going to be 3 squared. But in any one of these individual squares, the intensity will go down by the inverse square. So this, all of the light is going through here. And then all of a sudden, all of the light is going through 4 areas that you had before. And then all of a sudden, it's going through 9 areas. So this is going to be a ninth of the intensity that's up here. This is a quarter of the intensity, and this is the whole intensity. So that's why you've got intensity is the S, in this case, it could be P, it could be L. This is basically the power output, source strength, over 4 pi r squared. So the inverse square law is that the intensity decreases of the inverse of the square of the distance from your source. Not on the formula sheet, but in the specification. Thanks, examiners. Just making it tricky for all you people out there. And there you go. Just to put it into terms, the power output of a star is dependent, the apparent brightness as well is dependent on its distance, on its luminosity, on its temperature, and its size. Wien's law, Stefan's law, inverse square law, all deal with those interchangeable parts. And it's a really good suite of equations, which therefore you can work out exactly what's going on. That's what makes astrophysics so interesting. You can work out what's going on right at the start just by giving a couple of pieces of information and working it out from there. Okay, so back to the start again. So here we go. Now we've got Wien's displacement law. You might want to go on and stop the video and just write down everything you know about Wien's displacement law in terms of drawing the black body radiation, definition of a black body radiator and absorber, how they're linked to Stefan's law and the inverse square law on here, and how it's related in SI units and not in non-SI units, which is the other one there. Okay.